Welcome to Ladyada.
Hey everybody, and welcome to my desk. It's me, Ladyada. Did a bunch of tax stuff this week, so not a ton of hardware, but I did get some tester stuff working, and hopefully in a week or two we'll file our taxes, and we'll be done with that, and then we can move on to more hardware. So let's go to the overhead. I'll show off some of the stuff I was hacking on. So I did a lot this week as I worked on some testers, because there's a bunch of new products coming out. So the first one is the SHT45 Trinkey. So this board, I think I mentioned this a couple weeks ago. We have a lot of SAMD21 E18s in stock because we had to buy 2 years worth of stock, and then like we scheduled it out like, oh, send it to us every 4 months. We'll get like a quarter's worth, and every 3 to 4 months, and we're good for like 2 years. And then Microchip's like, anyways, we're going to send it all to you at once. And I'm like, I don't want it at once. And they're like, we're sending it to you at once, and it's too late. You already bought it. So I have a lot. So we're going to do a lot of Trinkies. So here is a SAMD21 E18 base Trinkey, which has a SAMD21 chip, a reset button, a NeoPixel, and an SHT45. And you see the little cutout. If you're using an SHT45, which is like a kind of a high quality temperature humidity sensor, I think it's like 1% humidity accurate. There's a little self-heating, so the temperature is like 0.5 degrees C, but it's like a little higher than ambient because it's measuring the heating, and especially if you have the heating element on, it's going to self-heat even more. But you might as well isolate it from like the LED and the microcontroller, so there's a little cutout to isolate it thermally, so there's no thermal conduction coming through the PCB. The only trade-off is now there's less dissipation for the self-heating. Is like you can't really win one or the other. Anyway, so this board's done, and so I decided to do the tester next because that's what we need to get it finished. The way this tester works is I use a little extension because this plugs in right into a USB port. And then, let's see, hopefully this tester will work. It's a live demo. It kind of like looks for the microcontroller. There's the SWD and SWC pins on the bottom. And then when you line it up, it's like, oh, I found your chip, good work. And then it'll program, and then it will test the output, and then it's done. So, and then this LED blinks to let you know every time it transmits data. So that the factory test that's programmed into this transmits over serial a CSV with like the serial number, because the chip has a serial number, the temperature and the humidity, and then whether the touch is capacitive touch is being touched. So pretty easy. But one of the things I had to do is, a lot of the originally the other Trinky code was still running on a TNC36, and because I can't get the TNC36 anymore. It's like I have too many SAMD21s and not enough TNC36s. I had to be Pico-fied. So this was Pico-fied. So it's great. So I'll get this in the store real soon. And also Pico-fied this ESP32 V2 Feather. So this is one of the board, I had to do a lot of redesigns. So I redesigned our classic Huzzah 32 Feather. And we were testing it with a Raspberry Pi, and that was like totally cool. There's nothing wrong with that. But the issue is that like people would accidentally unplug the Raspberry Pi, or like eventually like it had to F-sync or something. And so it was like not flaky, but I just wanted to have something a little bit more durable. So this this is only taking 9 seconds because the firmware's already been programmed, so I didn't have to reprogram the firmware. Did the test on a Raspberry Pi. The whole test takes like 19 seconds, 18 seconds, and then on this, if this was an erased chip, it would take like 26. So it takes like 10 seconds more. But I think it's worth it because again, like this is like solid state. Like there's no SD card that can fill up or fly across the room, or like get corrupted and whatever. So I think TAC did an excellent job with making this really fast. So it's pretty amazing. It's only 10 seconds slower, and it's an RP2040 that's bit banging with PIO, USB host, talking to the USB serial chip on here and doing the reset, sync, and program. And so it's like you're not going to get the highest speed USB CDC. You'll get 12 megabit in theory, but it's like there's still more delays than you will on the USB host control over Raspberry Pi. It's going to be much, much faster. One thing that TAC did implement, which I really love, is the stub and compressed firmware uploader. So on the ESP32, there's this thing called this, there's a built-in bootloader, and it totally works. And you can program without using a stub. But if you want, but then you have to send like every byte one at a time. And if you want to do it faster, what you can do is compress the firmware, like a gzip or whatever, or a zip, and then you send the compressed file over, and then it uncompresses and burns it. But you need to have a secondary bootloader, and that's called the stub. So this firmware on the RP2040 sends the stub and then resynchronizes and then sends a compressed version of the firmware. So it takes that like a lot less time, because the thing that takes the most time, well, erasing the flash takes time, but that USB to serial to the bootloader also takes a bunch of time. So this is all in the I think it's called the testbed library. So maybe I'll go quickly to the computer, because I'm sure people are going to be like, where can I find this? It's under test bed. So we did, publish everything open. So there's examples, not like the code for this exact tester isn't there, but there's code that's, very close. So, program SD card, program ESP32 from an SD card, or ESP over UART or CDC. So, you'll have to change your pins for whatever hardware you're using, but it does work. So that's kind of nice. And then the last tester I worked on, let's go back to the overhead, and then we'll get into the great search. So the last tester I did is for the HV, yeah, so this is the prototype, but the high voltage UPDI programmer. So we've already got the UPDI programmer in the store, and that just does like a plain 3 or 5 volt logic. The pin that's used for UPDI can't be a reset or GPIO. It can only be for UPDI, and that works great. But I did want to make a programmer that could do the high voltage pulse. So this board, I think you guys remember we designed this like a month or two ago. It has a 12 volt boost converter. That's the inductor and capacitor and the little chip. And then there's an analog switch here. An analog switch, like when you basically send an RTS pulse, it'll very quickly switch over to the 12 volts, and there'll be like a 100 microsecond 12 volt pulse, and then it'll go back to the USB serial data. So it's just when, you toggle RTS, and it sends this pulse, and then it gets you into bootloading mode. And it works great with the Arduino IDE. But as you can see, I kind of messed up the design because I forgot that it has 12 volts on the data line, duh. And so I had to make a couple changes. Since the parts are really small to see, what I'll do is, give me a second, I'll open up the tester. Let's see, where's the tester? It's called, sorry, one second. UPDI. How did I lose it? Oh, that's weird. Oh, here you go. All right, can you go to the computer? So many files. Okay. So the first thing I did is I read the serial data from pin 0, which is like the hardware UART RX. But obviously, I don't want the 12 volt signal to get into this pin, because even though the RP2040 is 5 volt friendly, it's not 12 volt friendly. There's nothing 12 volt friendly. So I've got this little Zener clamp here. And the way this works, here's the Zener clamp, is whatever voltage comes here, the voltage drop from here to this, which is no more than 3.6 volts. Remember the Zener diode, when biased reversed, it'll clamp at 3.6-ish volts. So I could have gotten a 3.3 volt Zener, but I happen to have 3.6s in stock, so I just used that. So if this is 12 volts, it's 12 minus 4, whatever, milliamps. But that gets sunk by the Zener, and so this voltage never gets above 3.6. Also never goes, of course, below 0, because this diode the other way will also reverse bias. The forward bias to be no more than 0.7-ish volts drop. So this protects the RX pin from the 12 volt signal. There's a little bit of like, it goes up a little bit with the 12 volts, but like half a volt. It doesn't go above 4 volts. That's good to go. And then here, so I also want to measure that 12 volt pulse, right? So I measure the UART data, but then I have to measure the pulse. The issue I had with this is in the on the board, we use like the USB bit bang on the RP2040. This is the USB host. So it's bit banging USB, and I actually set, I can over the CDC protocol say, toggle on the RTS pin. Maybe I'll show that really briefly. So here I can, I test the 12 volt by being like, okay, set the RTS false, set the RTS true, and then that'll cause the pulse. Then I have to read the analog voltage and I do the math, and then I just make sure that it's greater than 10 volts. The problem I had though is the teeny USB library was blocking enough, or it was delayed enough that by the time I told it, okay, toggle the RTS, and then I got back to the Arduino code to read the analog voltage, the time had already passed the pulse. The pulse is not that wide. So what I did is I made like a little peak, like it's not a sample hold, but it's a little like peak holder. So basically, it charges up this 10 microfarad capacitor through the 12 volt charges this 10 microfarad capacitor through the diode, but the diode has a low reverse leakage, and so the voltage can't leave this way. And then going through here, it's a resistor divider with 11 kilo ohms of resistance, and that basically causes the voltage to it charges fast because it charges quickly through this diode, but then discharges slowly. And so instead of getting a little pulse, it kind of turns into this like a long slid ramp. It gives me plenty of time to test. And so, now, connect over serial, it tests the serial data, it tests that the serial is self, reading, because UPDI is tied together through a 1K resistor. And then finally it tests the 12 volt pulse. It gets, 10.5 volts. It's good to go. So this tester's done. And I'm going to order new PCBs so I don't have this like crazy blue wire hacking, and that'll get into the store. Okay. So let's, okay, great. We're done here. We're done here. We're done here. So let's, let me show you one more last board, and then we'll go into the great search. 1 second. Okay, let's go to the great search. We'll talk about this board.
Where in the world is that part I need? The great search with DigiKey.
The Great Search brought to you by DigiKey and Adafruit. Every single week, Ladyada uses the power of engineering to help you ESP find things on digikey.com. Ladyada, what is the Great Search of the week this week?
Okay, so this week, for folks who remember, like about a year ago, it was a year ago, we did the great search on getting high-powered infrared emitters. And we made this board that has a right angle and like a vertical and a horizontal emitter, so that you can just blast IR for making like TV guns or infrared remote mimickers, or just you want to illuminate IR somewhere. And this has been working great. I love this board. It's all good. But then we had a request from the internal team to make the opposite. I want a receiver, something that receives infrared, because we have these like remote receiver. We have these little doodads, and they're wonderful and everything, but they're really hard to mount, and you have to like solder these little wires, and like, I mean, they work great and everything, but folks wanted something that was like plug and play mountable, maybe even has a little LED to tell you that the signal was received, a little debugging information. So I, oh, this is not a right angle break beam. This is a design that I came up with. So it has a right angle receiver and a vertical receiver. And then there's a switch to go between the two. And the reason there's a switch, like why don't you just tie them together, is because they're push-pull, and I don't want the outputs to fight each other if one's getting a slightly different signal, and I don't want them to corrupt the signal. So you just decide, did you want the vertical style or the horizontal style, which is cool and everything. But one thing about these receiver modules, these are like the SMT versions of that through hole, is that they're fixed in their frequency, the carrier frequency, which is like 99% of the time 38 kilohertz. But sometimes it isn't. Like some people have like remotes that are 50 kilohertz, 40 kilohertz, like 28, whatever. And even though these have a little bit of fluctuation, they're definitely not going to go to 45 or 56. Like there's limitations. And so I was reading about learning remote receivers that are, they don't do the full decoding, but they will give you the carrier signal modulated. So they'll just kind of, they'll at least give you like the cleaned up, they'll basically give you what you set to the IR LED with the carrier wave in place so you can determine what the frequency is. And like there are situations I think that this can be really handy. One, when you want to get like the raw signal from the IR, but also maybe like, you know, there are I think like programs for like Raspberry Pi or whatever that can do IR remote learning, so you can learn about the remote and then duplicate it, or they're repeaters. So I thought that could be kind of interesting. And we actually had, and you know, as it what's funny is like I love like when I research something and then like one of the links is to learn, and I'm like, whoa. So like Chris Young did an infrared. He did, sorry, I gotta find where it is because he did a lot of remote projects. This one. So it turned out he actually was using a TCMP learner chip, because somebody linked to this. So this was really cool. I was like, well, what is a learner chip? And then you like read the data sheet. Basically, like I said, it has a wide band of receiving. So let's go to DigiKey and find a wideband infrared receiver. So let's look for infrared receiver. I before E except after C, guys. Okay. Photodetectors, remote receivers. So just go to the category. Okay, 1342. And then what's nice is that I was like, whoa, like, yeah, here's the center frequency. Remember I said like almost all of them are 38 kilohertz, but there are some that go above and some that go fairly low. And then there was like, there was one that you could select the center frequency. And I was like, bomb, I'm done. Then I was like, this is gonna be the shortest great search in the history of great searches. And then I was like, wow, there's even some in stock. Chip shortage is over. So I clicked on the TCMP 770000, and I was like, this is really cool, because yeah, it will give you the modulated output. That's their thing. They're like, there's a little bit of delay, but they'll give you the modulated output. It's good from, you know, a wide range of wavelengths. It does 840 and 940, and you know, even up to like 1000 nanometers. Easy pick and place part, but it's no longer manufactured and not available. But there are substitutes. What's interesting is the substitutes did not show up here. So if you look, there was only one, well, two. There's the TR version, the TT version down here, and like this one, but there was no others. So what I did is I was like, well, okay, let me look at what's going on. And I was like, well, there's like the TC. I was like, oh, there's TCMP 59, 960. So there are a couple options, including one that was the through-hole version that was in that guide. But then I was like looking at this, and what I didn't understand was what was all the differences? Because if you search for, and like how did, like, was 96 like the strength or the frequency? And I didn't really want to dig through all the data sheets. So what I ended up doing is I found this document on Vishay, and they make like the most infrared receivers. Like they kind of run this place. And thank you, Sebastian Schaefer, who did a really nice job of explaining all the part numbers. And this is like a great document. I rarely see this, where they really explain like what every number and letter means, because then you know what you're searching for. So the application, and they're like, oh, if it's TCMP, that means it's a learning remote. And I'm like, great, that's exactly what I'm looking for. And then they have this like IC type, which you could ignore. And then I was like, well, what is the 96? Like there's 96, 95, 90, whatever. So the first number is the package. And I don't know if they have the photos of the package. They don't have the photo, but like all the different shapes are different. They have like different names for them. Like Heimdall, who's like a Norse god, and Bellowbog, which also sounds like a Norse god, but I'm not sure. And then like Winnie Moldcast. So I guess like package information. And then the auto gain, I'm assuming this is automatic gain circuitry. So it's like how it does gain detection. And then the frequency. And so we want 00 because there's no band pass. It's like it lets through anything within that frequency range. So if we go back, well, let's actually search for TSMP, right? Because we learned from this that anything that's TSMP will be a repeater or learner part. And let's now look at active, because like we've learned some are not available. So it's apply. And then, you know, there's different sensing distances, but maybe that doesn't matter. And this is the thing, they do have a center frequency, but like the categorization doesn't realize that the frequency is wide. You know what I mean? It's like the center is 38, but it's like it doesn't narrow band, it's a wide band. That's okay. So a couple different options. So it looks like all of them are like TS. Well, let's look at the ones that are just like normally stocking, because there's only like a couple. So there's 95, 98, 96, and then another 98. This is 98, 100, 98, 00. So let's look at it. So 9, TSMP, sorry, 996. Wait, that's weird because they said the package is, but the package is different. I think, oh, 9, sorry, this number is this 9. It's a silane IC. I don't know what that means. It must be some process thing they've got. So these are all silanes, I think. And then 96000. So they're fixed gain, no learning. So yeah, the number here, sorry. The first number is just the TSMP means learning, 9 means the chip ID, and then the next number is the package. And then this one has a 100 in it, and looks like that has a slightly different automatic gain, I guess. Well, we're not going to pick the through hole one anyway. So let's pick the SMT. Surface mount. And then apply. So the surface mount will have a lower, guess they don't have as wide of a gain. They're only good for like 2 meters or so. But that's okay. And then looks like there's 2 versions. I actually tried to figure out like the real big difference between these, but I like one is just a little bit smaller, but the gain is about the same. But the price is a little different. This one is a little bit cheaper in quantity. This one's, I don't know, they're kind of like the same thing, same frequency, like the same dish. So but they're both pretty good. But I think I'm just gonna go with, what's interesting is also this is 5 meters and this is 2 meters. But I think I'm gonna go with the 96,000. So yeah, this looks kind of nice. I like that it runs from 2 to 5 volts. And yeah, it's very simple carrier output. So you just have to clean up the power supply. And then when you get the signal out again, you're going to have to do your frequency counting to figure out what the frequency is. But I think this can be interesting. So I'm going to make a breakout for one of these as well. They have a vertical. One nice thing about the Vishay parts is they have 2 versions. There's it's like the pins they go around. So there's a right angle version, this one that sticks at the end, and a vertical version you can see that sticks up. It just depends on how it comes on the tape. Anyways, this is my pick for the Great Search.
And that's the Great Search.
Where in the world is that part I need? The Great Search with DigiKey.
All right, that's our show this week. Don't forget show and tell this week, and also Ada Box 21 unboxing. See you there.
Thanks
for
everybody.
spending your Sunday night with us, everybody.
Bye, everybody.